Good afternoon, and welcome to today's Electronic Design webcast. Our topic today is NTC 101, Negative Temperature Coefficient, Sensor Basics, Technology Comparisons, Applications, and more. Sponsored by Digi-Key and TE Connectivity. I'm Bill Wong, Senior Technology Editor with Informa's Design, Engineering, and Sourcing Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit the F5 key to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides by clicking on the green folder icon in the toolbar beneath the slides. Now let's meet today's speakers. We have a lot of Bills today, and Bill Howard is a product manager for TE Connectivity Temperature product line, having previously served as engineering manager with the company. His 26 years of experience engineering sensor systems and providing custom solutions for temperature measurement applications includes leadership roles in the Beta Therm and Measurement Specialties legacy product lines, which are now part of TE. He has a PhD in material science and a wealth of experience in manufacturing technology. Bill Machuga is a product manager for temperature sensors at TE Connectivity. He has over 28 years experience in the temperature field. Prior responsibilities include sales, engineering, product design, and custom applications for Fenwell Electronics, Inventus, Beta Therm, and Measurement Specialties. And now let me turn things over to our presenter. Gentlemen, the floor is yours.
Hello, this is Bill Howard. We're having a little bit of technical difficulty. I'm going to jump in here to take the starting part from Bill Machuga at this point. And we'll start off with just some basics of the NTC Thermistor technology. So what is an NTC Thermistor? NTC stands for Negative Temperature Coefficient, and Thermistor is short for Thermally Sensitive Resistor. These are ceramic material. It changes its resistance as temperature increases, usually used as a two-wire device, often found in a packaged form. And there's a lot of advantages in temperature sensitivity sensing for NTC thermistors. I mean, these include miniature size. They can be made very small. They've got good long-term stability. They're very accurate. They have high precision. There's a simple NTC circuit shown at the right. You can see that the implementation is quite simple as a bridge or as a Wheatstone bridge, where you're simply measuring the voltage across the thermistor device. So how does it work? Already mentioned that it's negative temperature coefficient. That means as the temperature goes up, the resistance value is going down. Again, semiconductor ceramic material. As you notice from the slide, very nonlinear device. So you're going to have an area of high sensitivity down at the lower temperature, and it gets relatively flat as you go up in temperature. Because it's a ceramic device, there's a lot of opportunity for us to change the formulation as we're making these parts. And we can formulate it so that the area of maximum sensitivity occurs at different temperatures. If you look at the large chart, you can see the red curve on the left. That's a part that has very low resistivity at room temperature, but as you go down in the sub-zero range, you have an area of high sensitivity or high slope to that curve. And as you move to the right, you'll see the The dark blue, this is a part that would be commonly used in the 0 to 50 degree C range. The lighter blue, you've got a part that's got higher sensitivity up in the 50 to 100 degree C range. And then you've got another in the yellow curve at the far right, a higher resistance part at 25 degrees C. But once you get up into the 100 to 150 degree range, you've got a part that's got good sensitivity and it's coming down into easy to measure range. Some people like to look at this in the log linear format, or even log versus 1 on T, to get easier to visualize representation of the curves.
Okay, I think I've solved my technical difficulties. This is Bill Machuga speaking now. Thank you, Bill. Converting resistance values to temperature. A thermistor is a basic dumb device. It is simply a resistor. It changes temperature with a change in temperature. And the different resistance temperature curves have different resistivity. The alpha is the % change in resistance per a specific change in temperature, measured in how much of a resistance change per 1 degree centigrade. Different way to define the same parameter is the beta relationship, which is a function of 2 different temperatures and a ratio. Lookup tables will define the resistance temperature curve, and the Steinhart-Hart coefficients are a mathematical formulation that is more accurate. So that's why we have the good, better, best, depending how detailed or how accurate you want to define the curve. The alpha coefficient is different for every resistance versus temperature curve. There are different resistivities of the material. Low resistivity materials will be used for low resistance temperature products. And the lowest curves are in anywhere from 100 ohms or lower. And we have different resistance curves that go as high as the megohms. The different resistivity allows you to build different resistance values with roughly the same physical size of the sensor, which makes life easier for the packaging and the manufacturer of the sensor. A low resistivity material will have a low alpha. 100 ohm material would be in the area of 3.5% change in resistance for a 1 degree C change in temperature at 25 C. A 10 K ohm thermistor jumps to 4.4%, 100 K ohm to 4.68, and a 1 megohm sensor, a high resistivity, would have an alpha of around 5.1% at 25 degrees C. And just to point out, the industry standard for referencing NTC thermistors is 25 C, no matter who the manufacturer is or where they're used. Everybody references 25 C just as an industry standard. The beta value is a more defined way to define a resistance versus temperature curve. It's based on 2 or 3 coefficient polynomials. And different curves are measured by referencing 2 temperatures. It's important to know when you can't simply look at a beta value and assume that a curve is the same or different from another curve. A 2585 beta value of 3977 is the exact same curve as a 050 beta value of 3892 or 25125 of 4012. When you're comparing beta values, you need to make sure you're referencing the same reference temperature points. This is an example of a lookup table for a 5,000 ohm sensor built to a resistance temperature curve with a beta value of 3976. What's important to notice in the RT curve, we're showing the nominal resistance, which is the actual published resistance temperature curve. The min and max resistance values are a function of the resistance tolerance and the beta tolerance. if we had the same curve and a different resistance tolerance or beta tolerance, the min-max numbers would be different. In this particular case, the temperature accuracy reference of 25C is plus or minus 1%. That 1% equates to a temperature accuracy of 0.23 degrees C. If you were to reference the temperature accuracy at 0 degrees C, it's a temperature accuracy of 0.197 degrees C. Because of the higher alpha at 0, you're actually getting a little bit more accurate sensor at 0 degrees C than you are at the reference temperature of 25. Conversely, if you look at the temperature accuracy at 30 degrees C, only 5 degrees away, the alpha drops to 4.26%, and the temperature accuracy of this sensor decreases to 0.3 degrees C. So knowing the temperature of the application is very important in specifying the accuracy of the sensor. You're able to achieve very good accuracy by specifying the tight tolerance in your working temperature. The Steinhart-Hart equation is a relationship for determining the resistance temperature curve from known measured resistances. It's a 2 or 3 equation polynomial and a coefficient polynomial, and you're able to get very good modeling of a particular sensor by plugging in the coefficients into a Steinhart-Hart equation. The Steinhart-Hart equation has ABC coefficients that if an application requires, we can calibrate a sensor at 3 points and generate an exact curve for that particular sensor without concern for a beta tolerance, because we're essentially taking the tolerance out by giving you exact measurements. Different ways to specify the characteristics of a curve, the beta value, the alpha or slope. Different manufacturers manufacture RT curves with proprietary formulations. Everybody has their own secret recipe on how to manufacture a curve. There are some industry standards that are used by multiple manufacturers, but we all have our own special recipe on how to achieve those. TE Connectivity has acquired several thermistor companies, one being Beta Therm, which would be our curve number 3. TE YSI Sensors has the exact same curve, and they call it their B-mix. Another third manufacturer might call it their C curve or the number 12 curve. That's just a reference number. To make sure you're talking about the same resistance versus temperature curve, you really need to define by the beta value. Different ways to specify the accuracy of an NTC sensor. One is a point match, where you're simply identifying an exact tolerance at a specific temperature point. In this example, 15,300 ohms plus or minus 2% at 0. If a customer has an application where they're making ice cubes, they're primarily concerned about the accuracy at or around 0 degrees C. There's no reason to overspecify the sensor and hold an accuracy over a range, say 0 to 50 or 0 to 70. Conversely, if a customer is making a coffee pot, they don't care what the accuracy is at 0. They may be concerned primarily at 85 degrees C or so. So knowing where you want to specify your accuracy is very important. If it's a specific application, a point match might be the most economical way to go. We have interchangeable sensors where we're holding a defined accuracy over a specific temperature range. In industry standard temperature ranges are 0 to 70 degrees C. It's very easy to hold an accuracy of plus or minus, say, 0.2 degrees C over that entire span, or 0.1 degrees C. For tighter medical tolerances, typically 0.05 degrees C is desired, and that's achieved over a smaller bandwidth, typically 32 to 44 degrees C. So knowing the application is very important in defining how you're going to define the accuracy of the sensor. You don't want to over-specify, that adds cost to the application, and you certainly don't want to under-specify. This slide's an example of different defined temperature accuracies. In the blue, we're showing an accuracy of plus or minus 0.1 degrees C over the span of 0 to 70 C. You can see it's a very, very tight distribution over the 0 to 70 range, which is 0.1 degrees C. And at the end of that range, you'll get what we call a bow tie effect, where the accuracy is not measured, and will start to drift to a looser tolerance at both ends of the spectrum. The orange graph shows a 1% resistance at a single point of 25 degrees C. So the bow tie effect begins right at 25 degrees C in both directions, where you see the temperature accuracy open up in both directions. And the green graph, shows a 5% tolerance at 25 degrees C. And that one, really defines what happens outside of the reference point. For the 0.1 degrees C at 100 degrees C, the accuracy is roughly 0.3 degrees C. Not much of a deviation from specified. In the 1% orange graph, 100 degrees C accuracy is 1.3 degrees. And in the green graph, the tolerance would be plus or minus 2.5 degrees at 100 degrees C. If the application required accuracy at 100, we simply wouldn't specify it at 25 C. We'd specify it at 100 to get your tightest bandwidth. This slide simply shows the graph of an interchangeable part where our standard items are 0.1, 0.2, 0.5, or 1 degree C over the span of 0 to 70. Thermistors being nonlinear. You can see the bow tie effect outside of your reference temperature range. At this point, we have a poll question for the audience. We'd like you to participate and just answer one simple question. Are you considering using temperature sensing technology? And if so, what type? We have resistance temperature device, which is typically a platinum sensor, a thermocouple, a digital sensor, infrared, non-contact, or other. Give you a second to just click a box and hit submit, and we'll move along quickly. At this time, I'm going to turn it over to Bill Howard again. Thank you. Apparently we're having more technical difficulties. I apologize for that. We couldn't hear Bill Howard.
Sorry, I'll jump in here, Bill. I'll jump in here,
okay.
Bill. Yeah, sorry. Hi, on this slide, we'll focus on the technology comparison, and we'll focus mainly on the pluses or the minuses. And we'll go down that first column of NTC Thermistors. And the first thing you come to is the negative of being a nonlinear device. I mean, obviously, with the age of microprocessors, you can input a lookup table or use equations, as Machuga has pointed out before. So that's not as much of an issue as it was in the analog age. But you go next down to the up arrow, which is your accuracy, and that's really the strong point of the NTC Thermistor, where you can get a device that's accurate to 0.05 degrees C over an extended temperature range for a relatively reasonable temperature, relatively reasonable price point. And the reason you get that is, again, the next plus, the high sensitivity. 4% per degree C is a huge change in resistance for 1 degree of temperature change, and that's a relatively typical value. And the knock-on effect of having that high sensitivity and the resistance range of 1 k ohm up to a mega ohm is the next plus is you can really ignore lead resistance effects almost completely. You can have 100 feet of extension wire and not need to make any compensation for that in order to get an accurate resistance reading off your device at the far end. Now, if you move to the right, same thing, the lead resistance effect. That is something that you really have to be concerned about with a platinum thin film RTD or a platinum wire wound RTD element. And that's going up. You need to be concerned about that because the sensitivity is only 1/10 that of an NTC thermistor. So now you've got to use a 3-wire or 4-wire configuration and compensate for the lead wire resistance if you want to get something that's an accurate reading on the device. Some of the other pluses, you've got an extended temperature range with the platinum. You've also got standardization. There are the PT100 and the PT1000 devices have DIN and IEC standards associated with them. So you can buy many off-the-shelf controllers that have inputs already programmed for PT100 or PT1000. Again, moving to the right with thermocouple, you have that same advantage for standardization. Thermocouple is a very old measurement technology, so there's a lot of controllers pre-programmed to handle a thermocouple input. And that largely negates the negative of the nonlinearity. Again, thermocouple is very nonlinear, but they do have the advantage of going into the thousands of degrees for their temperature range. One of the disadvantages, they are a low millivolt output. You do have to be concerned about electrical noise corrupting your signal. And in addition, it's not an absolute temperature measurement device. It's relative temperature measurement between the hot side where you've got the 2 wires joined together and the cold junction where you're measuring your voltage. So you actually have to have another measurement device, typically an NTC at the cold junction, to find out what that temperature is so you can determine what the temperature difference is and get your absolute temperature measurement. If you move further to the right to the semiconductor sensors, the digital and the semiconductor, these are quite similar to NTC in terms of their pluses and minuses, and we see some trend towards our digital devices in the market. Really, it comes down to a choice in terms of what type of output do you want. Do you want a digital output, or are you happy with an analog implementation with an NTC? Our digital devices have been covered in a previous webinar. Then let's just jump down to the very bottom row, which is cost. And we haven't put any absolute values of cost in here. We can be competitive. Let's see where slides are moving around here. Depending on the application, there's competitive solutions for any type of these measurement technologies. Then they range anywhere from dimes to dollars. Please hold on one moment while we get our slides in order here. Okay, this is pretty much a rehash of the sensor comparison, but what we will look at here is the center row of bubbles and really focus just on the ruggedness feature of the different sensors. You know, an NTC thermistor is based on a ceramic chip. So, you know, ceramics generally are thought of as being brittle. I mean, you can damage them. They can be fractured. there are some environmental effects. So it's fairly accurate to rate this as a 3 out of 5 in terms of ruggedness. It's never going to beat your thermocouple, which is the next one over to the right. Thermocouple is just 2 wires welded together at one end. Very tough, very rugged device. You have to go to higher temperatures and adverse atmospheres in order to really affect a thermocouple adversely. You know, a platinum reference temperature, a platinum RTD device has a relatively high degree of ruggedness, perhaps overrated in this slide in that if you bang them around for a wire wound or a reference RTD, they're going to be damaged, and the thin film devices can be influenced by strain, asymmetric strain, because they do have strain gauge effect. The fourth column over, thermopile, we're really not going to cover here. Those are your non-contact devices for measuring forehead temperature or temperature on moving devices. Then all the way to the right, again, touching on those digital devices, again, very similar to NTCs in terms of their strengths and weaknesses and the ruggedness. And again, mainly your temperature limitation with those types of devices, where you can't go over 125 degrees C without affecting the underlying semiconductor. If you just take a quick look at the bottom row applications, we're going to focus mainly on NTC. You see dialysis called out, again, great for medical range. It's right in the sweet spot for the temperature range of our devices, and we have high accuracy there. The appliances like some cookers and refrigeration devices, also a good application. When you look at HVAC, NTC is a very cost-effective for ambient to boiler temperature range. To take advantage of the real strengths, the precision and the sensitivity, that's where your industrial temperature references and your calorimetry applications come into play. Okay, at this point, I'll turn it back over to Bill Machuga to talk about some of the discrete NTC product forms.
Okay, the different product forms. We start off with a bare chip thermistor, and which is the picture on the far right. It's a metallized ceramic, metallized top and bottom. If we're going to solder leads to the device, we typically use a silver metallization. We also have gold metallized chip thermistors and N-band surface mount thermistors. We have lots of leaded devices. Typically, we would solder the leads to the device, and then if we're going to epoxy coat, we're able to trim those sensors to a very, very tight accuracy. You know, 0.05 degrees C for the medical range, 0.1 for the industrial, 0.2 degrees C for industrial standards. And we're also able to package them in high temperature applications. We have the axial lead DO35. We simply package the die inside the DO35 package. That's a very rugged, hermetically sealed device, typically rated to 300 degrees C. We also have radial leaded glass devices, which are also rated to 300 degrees C. Very difficult to get the same accuracy in a glass device than an epoxy coated device because we're not able to trim them to the tight tolerances due to the high temperature of the glass sealing. But we are able to get very stable parts with the hermetically sealed glass parts, which are also very good for rugged environments of high humidity, moisture, and situations such as that. Moving on, discrete sensors for packaging into assemblies. Very easy to package these sensors into assemblies, either axial or radial leaded. Packaged assembly will, upon equilibrium, achieve the same temperature accuracy as the discrete sensor. Another advantage of a packaged sensor is you're increasing the power dissipation of the assembly, which is very critical to make sure you're not generating an error in a sensor due to self-heating effects. So the more mass you have, the more power the sensor can have. Just a design requirement to be aware of. The base qualified sensors are either built to the Goddard Space Flight specification or European Space Agency specifications. We do have off-the-shelf parts. We're qualified on both, and Annual testing maintains the certification, so when you buy the part, you get the space qualified component. Leadless chip devices and semiconductors are used in hybrid circuits, high volume applications, pick and place applications, typically very low cost applications, board mounting temperature sensing. We have different series of discrete NTC sensors. A Series 1 sensor is simply an epoxy-coated part with a 32 gauge radial lead. Series 2 would have an insulated lead. The Series 3 and Series 4 have a slightly higher gauge lead material, either 28 or 30 gauge, to increase the power dissipation. We also have an MBD series, which is packaged, we dice the die into a rectangle as opposed to a square, and pot that into a polyimide or mylar sleeve that's very rugged and offers the same temperature accuracy, very easy for packaging into assemblies. It's a radial leaded device. We have our MCD series, which is our micro beta chip series. These were designed specifically for medical catheters, but they've since become very popular in other applications where very small size and fast time response are required. The OD of the MCD sensor is only 0.5 millimeter. And all these epoxy pots are rated to 125 or 150 degrees C and accuracy achievable of 0.1 degrees C or better. The Geo35 or the radial leaded glass, higher rated applications, hermetically sealed, very stable, and again, easy to package into different applications. I believe Bill's going to pick up the reliability.
Yes, I am, Mr. Machuga. Thank you very much. Okay, in this section, we'll look at some of the main factors that are affecting longer-term performance of the devices. So a sensor is inherently an unstable material. Interesting things happen around points of instability, and so the art of making a sensor involves keeping that material in its design state so you can make use of its unstable characteristics. And what that means for the user and for NTC users in particular is they need to understand how accurate their device is going to remain in the long run. So if you look at the graph, you'll see that this is the change in resistance over time at various temperatures. And you can see that, yes, the resistance values tend to drift upwards over time. That's referred to as aging drift. If you go from top to bottom on that graph, you'll see that at 125 degrees C continuous use temperature, you get fairly significant measurable change in resistance value over time. And as you go down to 100 degrees C, the rate of change becomes smaller. And then once you get down into the 75 degrees C range, that orange curve at the bottom, it gets somewhat difficult to measure and detect how much drift is going on. You'll also notice that the rate at which this change occurs continually decreases in time as the parts approach an equilibrium point somewhere out in the future. So manufacturers, when they make these ceramics, they use special ceramic processing techniques to ensure a high quality, low porosity, a high density part. TE spent a great deal of effort to create a high density, very high stability, high quality ceramic material, and that's really the core of creating a stable device. And then there's aging or stabilizing treatments that are done at or near the upper use temperature of the device, which moves them up this curve to a point where the remaining amount of drift that you would expect to see from the device is minimal, is going to have minimal impact on the end user. So let's look at some of the actual values, stability numbers. And one of the first things I want to point out is that what you're looking at here in the table are maximum values, not typical. So if these are for some of the specific products that we offer, these are the maximum ratings. Okay, so you can ensure that you'll be within this amount of drift over the given period of time. And we'll start with the top table and do a left to right comparison, looking at epoxy coated versus glass our glass super stable parts. And you can see that for all of these devices, below 70 degrees C, again, very little, hardly measurable drift at all. It's really only when you get up into 100 degrees C that you start seeing measurable drift in these parts. And, okay, look at the epoxy-coated, 0.2 degrees C at 100 degrees over 10 months. For some applications, that's pretty important. For others, you wouldn't care. But now when you get up to 150 degrees C with that same epoxy-coated device, you've got 1.5 degrees C of drift over that period of time. That's going to be significant for most applications, and that's why most of our devices are rated at 125 degrees or lower if they're an epoxy-coated device. Now you compare that, you'll go across to a glass-coated device at 150 degrees C. You've only got 1/10 of that amount of aging drift over that period of time, 0.15. And then for our super stable devices, it's, again, even lower than that. Now let's do a top table to bottom table comparison. The bottom table is 100 months or 8 years of drift, okay, a very extended period of time. Just look at the 100 degree C value for an epoxy-coated device. Now you've gone 10 times longer in aging period, and you've had less than half as much additional drift. So that's, again, an indication that these parts, as they move along their aging characteristic curve, they become more stable and they're approaching an equilibrium state. You'll also notice that the glass superstable devices over a 100-month period, even at 100 degrees C, only 0.03 degrees C of drift. The superstable devices get special materials, special processing, there's screening processes that go on. Yes, they're a more expensive part, but they're excellent for use in metrology standards and secondary reference standards in industrial systems. Their higher sensitivity around room temperature makes them superior to some of the platinum devices if your measuring range is within the range of these devices. Again, the measuring circuitry that's involved in these is much simpler than you need for an RTD device of the same accuracy. Okay, let's look at some of the environmental conditions and how they affect reliability. And focus here on temperature limits. And again, this is mainly focusing on the maximum temperature usage. For the epoxy-coated devices, 125 really, and that's above that, you're going to get a drift which is unsuitable for most applications. Glass, 250, you can go to 300 degrees if you use plating or precious metal lead wires. And there are some premium special products that go to higher temperature. But what happens when you exceed the maximum usage temperature of a thermistor? Well, obviously for an epoxy-coated device, aside from the drift, you can get solder reflow. These are usually have a lead attachment with your tin silver solders, so you've got about a 213 degree liquidus point on those solders. If you reflow, you're going to get a large resistance increase. You could have open circuit failure. You could rupture that epoxy package. Exceeding the temperature, you're going to get accelerated drift on all of these parts. And what's the effect of that? Well, when you're going to read a lower temperature than your actual conditions. So if you've got a switch point device, your part is not going to switch off until it gets to a higher temperature. If it's a controller running an oven, the oven's going to be in a higher temperature than it actually thinks it is. And then with glass-coated devices, if you're operating above the rated temperature for an extended period of time, you can get some corrosion on the lead wires. And the typical thing that's going to happen there is you're going to end up with an open circuit failure. So those are the temperature limit effects. Now let's talk about water. Moisture-induced corrosion is a significant hazard to many systems. It's not confined to electronics. For physical systems, anything can be affected by moisture and water. But for electronics and NTCs in particular, the main phenomena we're concerned about is metal migration. Now that's an electrochemical process. That's where your metal ions, your metal that's used in the electrodes or some other part of the material, ionizes, becomes an ion, and then moves under the electric field influence, and then plates out on the opposite side. Now what happens is that the metals move across, and when they plate out, they form what's called a dendrite. And these are, if you look at them under a magnification, relatively pretty structures. They look like little Christmas trees or icicles that have formed on the anode of the device. And when those dendrites move and form and grow across the semiconducting surface, they can actually form a short circuit when they reach the anode. And they'll start to conduct significant current. They'll result in a lower overall resistance for the device. Because they're somewhat delicate, when they first form and form that short, they can often carry too much current for them. They act like a fuse, they burn out. But in an extended application where you have conditions that can form these, they're eventually going to form a hard short, and you'll get a circuit failure. You know, typically it's going to be silver migration across the thermistor die face. Less common, you can get some copper migration across the glass and some glass radial devices. Again, because the detection of this is low resistance and it can be transient, it can be hard to detect and hard to diagnose what's actually going on until you get a hard short formed. Just a rehash of what you need to have this metal migration occur. You need moisture, and we're not necessarily talking about condensing water, just really a high activity of water, enough of an absorbed layer for the metal ions to migrate through. You need an active metal, silver or copper. Silver is found on the electrodes of the ceramic chips, copper on the lead wires of glass-coated devices. You also need a DC bias above the threshold for metal ionization. And if you look at your electrode half-cell potentials, you know, that's somewhere in the range of 1 to 1.2 volts is where you are going to start driving metal ionization. You also need time. It's not a fast process. You typically, we're talking months to years before you get this occurring in conditions where you have that phenomena able to occur. And it can also be accelerated by contamination, ionic contamination like salts from handling or contamination of process fluids used during the manufacturing of the device. So prevention of this, again, you know, glass encapsulation, some kind of moisture barrier. In a probe assembly, we would recommend using a metal barrier usually to prevent water penetrating a device. If you're looking at lead wires, plating your nickel or gold, or even using a precious metal like platinum is a prevention method. Then for the current itself, or the DC bias itself, you can use an AC measuring circuit. It's not very common. It's harder to implement, but it does pretty much negate the metal migration phenomena. You can also power down during the idle state when you don't need to make a temperature measurement to limit the amount of time that the power is applied across the device. And then it really comes down to careful bridge circuit design to limit the amount of voltage that's across the device. Again, when you look at time and controlling the amount of time that you're actually turning on device, it's obviously not an issue if you've got a disposable device or one in which you have a very limited expected life of the component. And then good manufacturing practice. It's really up to the manufacturer to ensure that they're not allowing contamination onto the part and they're doing a good contaminant-free cleaning operation before they go into their final encapsulation. If you got something like refrigeration, where you've got a part that's going to be powered up for a long period of time under an environment with a lot of ambient humidity, we really always recommend using a glass encapsulated device. At this point, I'll turn it back over to Mr. Machuga.
Thank you, Bill. I'm going to look at selecting an NTC thermistor for specific applications. Thermistors are used in everything out there today, anywhere from a low-cost sensor in a high-grade toaster to components on the space shuttle. And the packaging of those devices, the selecting of the optimum sensor for the packaging is critical for the application in terms of both cost and long-term performance and life expectancy of the part. Common medical applications, in a catheter, we're looking for a very small envelope dimension on that. I mentioned the MCD thermistor before, having a diameter of 0.5 millimeter. That's 20 thousandths of an inch. We're being challenged by catheter manufacturers to reduce that size, and we're working towards that as well. Dialysis equipment, you need a very fast time response in Typical packaging on those are in a metal housing because it's directly immersed into the liquid. Packaged in a 400 series stainless steel. Very thin wall where you're looking for a fast time response and very high accuracy. The less mass of the entire assembly, the faster the time response. Patient monitoring, we have both reusable and disposable sensors. Those are the 400 series, which is a legacy YSI product, where anywhere from pre-me temperature monitoring, which single-use devices. We have reusable devices as well for different surgery processes, different invasive processes. Typical accuracies in the medical range, we're looking at the 05 degrees C. So again, thin wall, fast time response for medical applications because they want to know if there's a temperature change rapidly. Appliance markets, typically you have two ends of the spectrum there. You have low temperature refrigeration and you have high temperature applications as well. Cost is a primary driver, so usually the high volume DO35 or for high temperature applications, a radial leaded glass sensor. Pull and spark controls, you simply need to package the device for the application. You're not going to get a very fast time response change in the application, so a larger probe more suitable for that. Maybe an overmolded probe with additional moisture protection. Industrial oven controls, they need to be working in a temperature range of around 300 to 400 degrees, 200 to 400 degrees F, but often have to survive a self-cleaning cycle much higher. That would be a high temperature application. Commercial coffee makers, residential coffee makers, clothes dryers. You're looking for long-term stability in those devices where the last thing anybody wants is a service call because of a bad sensor. So high stability glass is typically used in the appliance markets. HVAC and refrigeration, you've got air conditioning, airflow. You've got mobile refrigeration, tractor-trailer trucks, the Thermo Kings and Carriers of the world, fire detectors, building management, boiler controls are HVAC. You've got commercial refrigeration for supermarkets. We've got a large family of products used in those applications, from pipe mount sensors to airflow sensors, high accuracy, high stability. These applications very susceptible for freeze-thaw conditions. Moisture protection is very critical for long-term applications. Instrumentation, you're typically getting into a more precise measurement and a more stable sensor. You're looking for something that's going to be the same reliability year on year with minimal effect. As Bill had mentioned earlier, in some of the super stable glass is very suitable for the metrology markets. Same goes for the instrumentation market, where you're looking for comparisons or very, very small changes in temperature. You can't have a sensor that's going to be drifting in those applications, so stability is more of a driving force in the sensor selection. The aerospace industry, where we have sensors on satellites, any aircraft that fly, atmospheric monitoring, fast response for fire detection and control. We have the space qualified parts. Now, a lot of the commercial aircraft doesn't need a space qualified part, but they do need a reliable part. We offer parts with additional screening or special testing as required by the application or the customer requirement. Gold metallized chip thermistors are typically used in telecommunications applications, a lot of fiber optics, or laser control, where a change in the temperature of the laser will result in a different wavelength. A lot of temperature control and compensation are done with a gold metallized chip, which is packaged inside of a hermetic package. The defense industry, we have many applications for temperature monitoring of different systems that are on standby, so nothing's really happening, but there is temperature control, temperature monitoring, and so forth. The automotive industry. If you buy a new automobile today, you're going to get roughly 30 to 40 NTC thermistors on that automobile, anywhere from outside air temperature, cabin environmental control, you have front and rear, you have heated mirrors, energy efficiency of the engine, air intake, flow controls, solar load on the vehicle. Emissions are a very fast increasing market on NTC thermistors. So an awful lot of temperature sensing. You've got we have applications where we're controlling the temperature of the heated water in the windshield washer instrument. So it's more and more popular. We have sensors in heated seats and cooled seats in automobiles. The telecom industry, I mentioned before, the gold chips, crystal oscillators, EWM wavelength control. That market's been growing exponentially over the past decade. And we're back to another poll question. We'd like to know your immediate needs or how soon you think you might have a temperature sensing application for a thermistor. Would it be immediate, in the next few months, greater than 3 months, or no current plans at this time? Please take a second to submit and we'll move forward.
Okay, I'm taking over from Bill for advanced applications. We're going to have to move fairly quickly. We're very short on time. So briefly, what I'm going to say is that we do have white papers on our website that talk about each of these applications, and we're mainly talking about non-temperature sensing applications. So heat dissipation is the focus. That's the ability of the sensor to dissipate heat energy given in milliwatts per degree C. So you put in so much power, and you're going to get a certain change. Again, these heat dissipation is higher in liquids than gas, so that's your level sensing. It's higher in a stirred fluid or a moving gas than a static environment. That's your levels, your flow sensor. Higher gas densities, that's your pressure or vacuum gauge, and higher in different gas mixtures, so you can get a gas mixture sensor. Then we'll jump right on to, again, we have white papers on these on our website. NTC options, custom design options. So far we focus mainly on discrete elements, but all of our devices are available, packaged in different forms for different applications, overmolded in screw-in type mountings, in ring lug type mountings, or extended probe assemblies. And I think we'll jump right now into our Q&A session.
Great. Well, thank you. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of the screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So for our first question, does the thermistor accuracy spec include any long-term resistance change over time, such as resistance stability?
That's a very good question. Unfortunately, it does not. When a thermistor is specified to a specific accuracy, that is the accuracy that is tested to at the factory and shipped out the door. Knowing the environment and the application, we can predict future accuracy based on anticipated drift. But when you specify an accuracy, that's the accuracy going out the door.
Okay, could you talk a little bit more about sensitivity resolution parameters? Why is a higher value better?
I'll take that. It eases the requirement for accuracy in your measurement circuit itself. For instance, if you have a 16-bit A to D and you have a large change in resistance, it takes fewer bits to determine what your temperature change is. And it also allows you to ignore lead resistance effects.
All right. Could you talk a little bit about the math behind the conversion from percent tolerance to the actual temperature tolerances?
Again, that's mainly done with the alpha coefficient at a particular temperature. So you're using the percent per degree at a particular temperature to change from resistance to temperature tolerance. The conversion from a beta tolerance and a resistance tolerance at a single point is a little bit beyond the scope of this presentation. I don't think we have time to go into that in detail.
All right, here's a question regarding calibration method details. For high accuracy medical applications, what equipment or techniques are used for calibration? For example, if you need 3/4 points or for calibration using the Steinhart equation, are those points needed to be highly accurate? And is another more accurate temperature measurement needed? I.e., what's considered good practice in this area?
Well, again, your accuracy using a Steinhart calibration or the ABC coefficients is only going to be as good as the initial calibration used to measure those devices. And I think we covered on the slide that, using the 4-term Steinhart, you will be within the precision limits of that calibration. With the 3-term, you're going to be within 0.01 to 0.003 degrees. And again, that requires calibration in your temperature range that's at least that accurate or better.
Okay. What type of NTC thermistor would you recommend for medical thermometer applications?
I got that one, Bill. For medical thermometry, we're typically trying to make a sensor that's very accurate going out the door that is interchangeable. So what we would do is supply an accuracy, again, we're looking at a very small span, something in the area of 0.05 degrees C. We could supply a sensor more accurate than that, but we would have to do individual calibrations on that, and that adds quite a bit of cost. Typically, the 0.05 degree C accuracy is sufficient for medical thermometry.
Okay, we still have a lot of questions which we'll have to answer via email, but that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Digi-Key and TE Connectivity for sponsoring today's event, and of course, to all of you for joining us. Have a great rest of the day.